Okay, ladies and gentlemen, day 23 of the Cliff Lab. First problem, warm-ups. Number 1, ball rolls off a flat box that's 25 centimeters high. The ball rolls at 2 meters per second. Find the range. So we're going to be using 2 steps. First, we're going to find the time to drop, time to fly, and then we have a second part where we find the range. When we use the time to drop equation, the h has to be in meters. So that's why we converted the 25 centimeters to meters, 0.25. Divide, square rooterize, and you get 0.22. That's the seconds in the air. And then we use that time in the range equation. Delta x is the range, the difference horizontally, equals velocity times time. The story problem gives us the 2. We multiply by the 0.22 for the time, and we get 0.44 meters. Questions about that? Number 2. 2 researchers are debating a scientific issue. One says, "My theory must be right. If it's true, that would mean that we can prevent thousands of deaths every year. More children would be healthier and happier." Is this a valid scientific reasoning, or is it red herring? Right. We're bringing up some very emotional stuff about thousands of deaths and happy kids. That's emotional stuff. That's not about the data, about whether or not the theory is right. The researcher here is saying, if it's right, then we can prevent things. Okay, so it's not even about counting deaths or anything right now. That is a red herring. Before we turn to the lab, you're going to observe a ball rolling off a counter, and you want to predict where it's going to land. What measurements will you have to make when you watch the ball? Okay, so Lily, let's put away the games, please. We have here ramps. They're all pretty much exactly the same as best as I can do. And we have a steel marble. Okay, so we have this ramp. And you're going to release it from the top, and you're going to watch it roll down, and you're going to watch it roll across the table, and you're going to stop it before it leaves the table. What kind of measurements do we have to do in order to predict where the marble lands on the floor? Who can tell me? You're going to observe a marble rolling across the tabletop, and you're going to stop it before it leaves the tabletop. What observations, what measurements do you have to make in order to make a prediction of where it's going to land? You have to find the height of the ramp. Are you talking about this right here? Yeah. And then what would you do with that? The t equals square root? Okay, that's if it was falling straight down or falling through the air, even at an angle. This is not falling through the air at that point. So no, you will not need to find the height of the ramp here is not going to be part of the equations or measurements at all. Michael? We just did a story problem that is basically doing the same thing. Do we have all that information for this situation right here? Yeah. We need to find the velocity. So how do we find the velocity of a rolling marble? What measurements do we have to do? Yeah, you have to find the distance from the ramp, the bottom of the ramp now, to the edge of the table, because that's a consistent speed. Here it's getting faster and faster and faster and faster. We don't want to measure anything about this ramp. It's from the bottom of the ramp to the edge, yeah. So we have that in meters, but that's not the velocity. How do we get the velocity? Yep. Okay, stopwatch how long it takes to go from the bottom of the ramp to the edge. Use a ruler for the bottom of the ramp to the edge. Divide distance by time and you got yourself a velocity. What else do we need to know? Not acceleration. Look at the story problem. What else do we have in the story problem that we needed to know? The height that it falls. So the height of the tabletop. Again, it has to be in meters. Whenever we throw things into equations, they should be in meters and seconds and liters, the normal units. Okay, that's a general overview. Let's do some practicing though before we actually get to the lab. Okay, main ideas. We spent time reviewing yesterday. Any questions on homework that we've done so far? You're going to get a grade on participation with your lab today. When you get it all done, you'll get your points. And we're going to have, it's not homework 21, it's homework 23. Please change that 21 to be a 23. It's 10 questions long. Next quiz. I'm sorry to say, ladies and gentlemen, I have to change your schedule. I'm sorry, this is going to be a great disappointment to you, but we're not going to have the derivation quiz tomorrow. You're just going to have the quiz on day 25, Monday. That's the quiz on the packet, on the airborne information. It is not on derivations. I know you're very disappointed with that, but that's just the way it is. We'll have the derivation quiz, it turns out to be on day 69, a long time from now. Okay, today's purpose. You'll predict where a ball will land after running off the countertop. Relevance. This is how you apply the skills that you learned in lesson 2 of somewhat real-life situation. It really happens, but it's not a common occurrence. Success. You'll place a target at the predicted location on the floor, and you'll see if the ball lands where you think it does. Okay, Miss McKinney rides a tricycle at 30 meters per second off a cliff. That's 24 meters high. What is her range? Think about what is the first step in solving this problem. Write down the equation for the first step. Lily, what did you write down?
24 over divided by 4.9.
Yep. And what do you put in for the H, Julian? For the H, 24. So I have T equals square root 24 over 4.9. If you do your math on the calculator correct, I sure hope that you turn out to have 2.2 seconds in the air. Second step, write down the equation, please. Substitute numbers in. Christian, what's the equation? Okay, yep. Delta x, the range, equals the velocity v times time t. So we end up having 30 times 2.2, and we get 66 meters. That's a long distance through the air. Number 2, a little bit different. Number 2, a sharpshooter climbs to a 100-meter tower, has a rifle that is horizontally firing a bullet. The target is 2 kilometers away, gets hit. What is the bullet's average velocity? Notice that we're looking for a V here. We are not looking for the range. But the first step is going to be the same. Go ahead and write down the equation, substitute things in, and get a time of flight. What is the time of flight here? Michael? I get 4.5. Did you square root? Thank you very much. 4.5 after you take the square root. Okay, now the second step is going to use the same equation. Delta x equals VT. However, which variable are we looking for now? Marissa, which variable are we looking for in this equation here? V. So the V stays a letter. We put in numbers for the other things. We got to use meters, so we're changing the 2 kilometers to 2,000 meters. 4.5 is what we just figured out for the time, and you come up with 444 when you divide both sides. The next problem is just like it. Would you please spend a few moments doing that? Turn to your neighbor when you're done and compare answers. Questions, feel free to ask. Come on over. All right, here we go. Marco's not here. Alex, what's the time in the air?
Time in the air is 3.4.
Yep, I rounded it to be 3.5. Either way, I don't care. And Ethan Dickin, what is the variable that you are solving for in number 3? We're solving for V. So we put in numbers for everything else. And what do you get as an answer, Isaiah? Do you have an answer for number 3? James is not here. How about Cherie? I got 30. So we have 105 meters for the range. It lands that far from the base. And the time in the air is 3.5. So to move 105 meters horizontally during that time, you have to be moving about 30 meters per second. Questions on that? Alrighty, turn the page. Cliff Lab. Task. Predict where a ball will land when it rolls off a counter onto the floor. So you're going to do your measuring of various sorts. And then I have a plastic tray with a bunch of sand in it and some circles. That's your target. You're going to place that tray exactly where you think the ball is going to be landing. And then we'll actually test it out and see. Materials. We have the ramp, like this. I've already talked about this, I guess. Stopwatch, measuring tape, and cliffs. The cliffs are going to be just the countertops. We're going to break this up into 3 parts. First of all, find the velocity. This is only when the ball is rolling on the black counter. You are not measuring anything when the ball is on the ramp getting faster and faster and faster. Record it 10 times. Now it says here, put a single line through any outliers. So if you get like 1.5, 1.6, 1.5, 1.6, 1.7, 1.5, 3, 1.5, 1.6, 1.4, the one that was 3 seconds, something funky happened. Just draw a single line through it. You're not scribbling it out, making a big black blob. You're not erasing it or using whiteout. You're just making a line through it. Because who knows, maybe later on you'll discover, hey, that was a valid point. There's something funky going on because of this and this and this. And so you want the evidence and you want the data. At the very beginning of the year, you guys did a little bit of a reading about this chemist who talked about quasi-crystals, whatever that is. I don't remember. It's chemistry. I don't care. Neither do you. But the idea is, he proposed this idea of a quasi-crystal because he had some data to show it, and everybody laughed at him and kicked him out of their study groups and their little science clubs and stuff, ostracized him, and he had a hard time of life for a while, until finally, people finally agreed, yeah, I guess you were right. Here, have a Nobel Prize. Seriously, he won the Nobel Prize for chemistry in this thing. When people went back and looked at their own data from old experiments, they realized, oh look, we could have discovered that too. Our data showed that. We didn't realize it though. So you never know when you have to go back to look at old stuff. Okay, so that's about what that's all about. Once you find your average velocity using this equation up here, work it out. I want to see it. And then you're going to work out the time in the air using this equation. And I want to see it before you go any further. And then you're going to use those two pieces of information to figure out the range using that equation. And I want to see it before you test it out. Okie dokie. Questions?